Welcome to the Digital Evening at the Observatory. This broadcast, the first one in English and brought to you by a tiny skeleton crew, is provided by volunteers from the WLS, the Werkgroep Leidse Sterrenwacht, which translates to the Leiden Observatory Working Group. The WLS is an association with nearly 100 members. In addition to broadcasts like this one, we also host public evenings at the Old Observatory in Leiden. Furthermore, we maintain its historical telescopes and use them to observe objects in the sky. My name is Sarah. I'll be your host tonight. I'm also one of the speakers. The technical aspects of this broadcast are handled by Theo, who fulfills a dual role too. He is the other speaker of tonight. The subject of tonight's broadcast is ESA's JUICE mission. JUICE stands for Jupiter Icy Moons Explorer. In the first part of the broadcast, Theo will tell you about Jupiter's ice moons and the route the space probe will take. In the second part of the broadcast, I will tell you about what ESA hopes to discover with this mission and the instruments they want to use for that. During the broadcast, you can ask questions via YouTube's chat feature. We will collect these questions and answer as many as we can after each speaker finishes their story. So I think it's time to move on to tonight's first speaker, Theo. Theo has been a volunteer at the WLS for 7 years. He's one of the regular speakers at our Dutch Digital Evenings and at the public evenings at the Observatory in Leiden. Are you ready, Theo?
I'm ready. Good evening.
Take it away.
Thank you. Thank you, Sarah. Yeah, let's talk about JUICE, what it is all about. And you see a picture over here where in the distance you see the satellite JUICE. You see Mars, and you see some moons. The mission will take about 8 years before it arrives at Jupiter. The distance is not that long, but I will tell you why it takes such a long time before JUICE will arrive at Jupiter and its moons. Let's first have a look at our solar system. On the left-hand side, you see the Sun, then you have Mercury and Venus, then our own planet Earth, then you have Mars, Jupiter, Saturn, Uranus, and Neptune. And then further away, you have some dwarf planets, like before you had Pluto, but that's no longer a planet. The distance from Earth to the Sun is around 150 million kilometers. And the distance from Earth to Jupiter, that's on average about 700 million kilometers. We have the inner planets, which are rocky planets, and the outer ones are gas planets. If you look on the east, then in the next couple of months, you can see Jupiter. When you take a telescope, and on my right-hand side, you see a small telescope, and you see here a little bit of a moon, one of the moons. But this is how you can look through a telescope and you see the bands of Jupiter. You need some adjustment to the camera system, and then on the PC you can see this little bit turbulent planet, and that's because of the atmosphere from the Earth. When JUICE was launched on the 14th of April 2023, so a couple of months ago, you can see that ESA rocket took JUICE, and JUICE is here on top, and with a very heavy rocket, it was launched. And you see here how the rocket is going into the clouds. It goes through the clouds, and you can see here all the strength, and it opens up here this rocket where JUICE is, and then JUICE is taken away all the way down to Jupiter. The reason why it takes such a long time is because of the gravity from the Sun. In order to get more speed, they call it a kind of a flyby. And then the flyby is, the first one is from Earth. You see here JUICE, and Earth is pulling JUICE, in fact, with it. And every time that it has a flyby, it increases the speed about 10,000 kilometers an hour. So when it is launched, it's for instance 40,000 kilometers an hour, and after the flyby, it's about 50,000 kilometers an hour. And only in this way, JUICE can get all the way down to Jupiter. There's another way if you have a rocket which is 10 times stronger and more fuel, but that's even more difficult. So that's why they do all these flybys. To give you an impression what the flybys are, now let's first talk about the flybys. Then if you have here JUICE, it goes through an asteroid where it is a little bit of danger that one of those asteroids can hit JUICE. So it's not, let's say, without risk that JUICE do these flybys. And then when it arrives close to Earth, there's a lot of space debris, and with the space debris can also hit the JUICE, and that means that it could damage the satellite. But there is enough space between the asteroids and the space debris that they believe that the flybys can be carried out, and if you're very unlucky, then it will damage the satellite JUICE. To get an impression about the flight from JUICE, as I said, in April 2023 it was launched. It goes a long distance away from Earth, and then it comes all the way back to Earth with the Moon in August 2024, and that's the first flyby. So then it increases speed. The next flyby is Venus. That will be in August 2025. And then with this flyby, there will be another increase in speed. And then in September 2026, it comes back to Earth, and then it increases another 10,000 kilometers an hour, and then another last one in January 2029. Then it will have sufficient speed to get away from the gravity from the sun and goes towards Jupiter. It first goes around Jupiter, and then that arrives in July 2031. Then it goes 35 times around the ice moons from July 2031 till November 2034, and the last ice moon, Ganymede, in December 2034. And at the end it will crash on Ganymede, and that will be because there will be no fuel left on JUICE. The number of rocks and moons around Jupiter is tremendous, around 300, and 92 out of 300 rocks are the so-called moons. And all the other ones are smaller and is more a rock than anything else. From the 92 moons, there are only 3 that ESA is interested in, and these are Callisto, Ganymede, and Europe. But let's first look at Jupiter. Jupiter, as I said before, is a gas planet. The total weight of this planet is more than twice of all the other planets in our solar system. It has a wide band. This is the bandwidth you can see in the middle. It is of white because of ammoniac and water. And that's what you can see, as I shown in that little movie. Through a telescope, this band is clearly visible. What you can also see through the telescope is this hurricane. This hurricane is huge. The Earth easily fits in here, and it's already there for more than 300 years. The hurricane is very strong. The winds are something like 3,000 kilometers an hour. And on Earth, if you have a very heavy hurricane, it's around 300 kilometers an hour, even less. Jupiter has a north and a south pole. It turns around every 10 hours. It's making one turn, so one day on Jupiter only takes 10 hours. And it is much further away from the Sun than the Earth. It takes 12 years to make one round around the Sun. That means that a year on Jupiter is in fact 12 Jupiter years. It has no seasons because the equator is straight onto the Sun. Not like the Sun, not like the Earth, because the Earth has an angle of 23 degrees. When Voyager was passing Jupiter, it noticed that there are also rings around Jupiter. These rings are around 6,000 kilometers wide and 10 kilometers thickness. It's very difficult to see them. With a telescope, you don't see them. But of course, with the James Webb, these rings are clearly visible. On the north and the south pole, it looks like rings, but that's the reflection of the sun onto the gas. So this is not a ring and that is not a ring. But in the center, you see these rings. Let's then go to the first icy moon, Ganymede. Ganymede is the largest moon in our solar system. It's bigger than Mercury. It has an ice layer of about 90 kilometers thickness, and underneath that ice there is a bit of water, something like 10 kilometers of water. It has a lot of rocks and a lot of craters because of the asteroids hitting the moon. It has also tectonic plates, the same as on Earth, and the tectonic plates, the lava in there is causing heat, and that breaks the ice, and you can see here the scarps on the surface of Ganymede. The next one that Zeus will visit is Callisto. It has a lot of white and black spots. It's also rocky, it has mountains and a lot of craters as well. If you then look at the inside of Callisto, that's rock and metal, this black and white in the side. Then there's a layer of water, this purple one, and then you have this ice on top of it. But as you can see, it has a lot of ice and a little bit of water underneath there. It is different from the last icy moon. I will talk about Europe. That has a reasonable flat surface, although you see here some mountains and it has also craters. But it's a very interesting icy moon. And why is it so interesting? If you look at from the side, then you see here the ice layer, which is between 25 and 50 kilometers thick. Then underneath that ice, there is water. And that water is something like 65 to 100 kilometers thickness. The amount of water on Europe is larger than the total amount of water on Earth. Because of the lava and the heat underneath there, the ice melts, so that's why this is water, but it also cracks the ice. And you can see here a crack through the ice, and the water sprays like a geyser into the atmosphere. And that is shown on pictures taken by Voyager and by other satellites. And the interesting thing is that if you look at the conditions of Europe, with the water, the ice on top, and then the heat from underneath from the inner side from Europe, there's the same condition as on Earth, on Iceland, where you also have ice, water, and hot surface on the sea. And in the conditions on Earth, life is made, and you can see that under those conditions, there is a possibility that life could also be on one of those three planets, one of those three moons, Europe, Ganymede, and Callisto. How that is measured Sarah will tell you about that in the next presentation. So my thing is, what are there any questions? Let's see. Yeah. So
Yes, Theo, thank you for your presentation. That was very interesting. I see there are a few questions. Let's see if you have a nice answer for them. So one of the questions is, can juice prevent a collision with space debris in any way? You were talking about there's a little danger.
that is possible, yes. If you look at the amount of satellites launched in the last couple of years, and if you look at the satellites that are damaged and are in small pieces, which makes it thousands of small metal and other things, and it goes with speed of 50, 60, 70,000 kilometers an hour. If that will hit juice, it could damage it quite severely. But of course, there is still a lot of space in between the debris, so it's not that it will, let's say, the chance is too high. Otherwise, you wouldn't do that. But the
No,
risk
yeah,
is acceptable.
there's a lot of space in space, I'm told.
That's right. Yeah. So that's why, and also with the asteroids, the chance that it will hit an asteroid is very small.
Okay. Yeah, so let's see, another question. So you were talking about the moons of Jupiter, that's where the probe is going. But it's focusing on the ice moons. So there is another important moon called Io. And the question is, why not also focus on Io? That's an important moon too.
That's true. There are a lot of moons, and Io is one of them. But the conditions on Io is very hot. It looks like if the Io is a reasonable young moon, uh, let's say the surface is very thin, and underneath there is a lot of lava, and there are a lot of eruptions, and so that means that it's difficult to believe that there is anything like that, and also to land on Io. Io, with the eruptions, it has a lot of sulfur and sulfur dioxide, which makes it very hard also for the material to withstand that, let's say, corrosion conditions.
Okay.
So Io is not very attractive to be there.
Poor Io. Such
Yeah,
a pretty little moon. Okay, then one more question. Yeah, there's actually two questions that are related to speed, so I'll just ask them quickly. One of them is, how can a flyby of a planet change the speed of the probe so much? How's that possible?
Yeah, when JUICE arrives or is flying towards a planet, then of course the gravity of that planet increases the speed of the satellite.
Mm-hmm.
Then let's say the route from the planet is, let's say, on the picture is downwards. So it takes longer that the gravity will pull onto JUICE and increase the speed.
Okay.
Then when it leaves the Earth, it quickly leaves the Earth. So it goes with a shorter time that it is slowed down by the gravity from Earth.
Ah.
So you have a long pull onto the satellite and a short period that it will actually slow down. And the
Right.
result is an increase of about 10,000 kilometers an hour of additional speed.
Yeah. So in the end, when it arrives at Jupiter, do you know what the speed is then? Do you have is there
Well,
an
I read
estimate?
that every flyby, it increased the speed about 10,000 kilometers an hour. And I'm not sure if at the last time that it will have a flyby on Earth, that will still be 10,000.
Mm-hmm.
But I would expect it's between 80 and 90,000 kilometers an hour.
That's pretty fast.
And you need that, otherwise it will slowly go backwards and crash onto the sun, which is
Yeah, no,
not
that's
the
not what you
idea.
want. No. No, that's not the point of this mission. No. So yeah, so I think yeah, that's the questions that were here for you.
Okay. Well, thank you very much, Sarah.
You're welcome.
So the next speaker is Sarah. So we do this dual role. Sarah is already 3 years within WLS Association. She does the presentations on the internet broadcasting, and also she is the host of the internet broadcasting. She also works for Copernicus. That's another association, and she works also in space industries, and that makes it all very interesting and all very nice to have these, let's say, the experience of Sarah into this type of, let's say, internet broadcastings. So Sarah will be the next speaker. So I'll take myself away, and then I'll. Oh, it doesn't work.
So I think I can start. JUICE is primarily going to observe 3 of the 4 Galilean moons and Jupiter itself. But what exactly do they want to learn from this? And what instruments will they use? In the first part of my story, I'll answer the first question. So, what exactly do they want to learn from this? What do they hope to discover? JUICE is a part of ESA's Cosmic Vision program, the program in which ESA's scientific space missions are planned. The JUICE mission addresses 2 of the 4 main questions posed by this program, namely, what are the conditions for planet formation and the emergence of life? And how does the solar system work? The JUICE mission does this by zooming in on the 5 mysteries ESA outlines in this overview. First, let's have a look at the mystery on the bottom left. What are Jupiter's ocean worlds like? The name of the mission is Jupiter Icy Moons Explorer for a reason. An important part of the mission is about these 3 icy moons. They are the 3 Galilean moons that are thought to have oceans of liquid water beneath their ice crusts: Ganymede, Europa, and Callisto. The mission will have a focus on water. JUICE will investigate these oceans to see how far below the surface they can be found and whether they are fresh or salt water, and how much water they contain. The estimate now is that the oceans on these 3 moons together could contain 6 times as much water as the oceans on Earth. Geological activity. The surfaces of all 3 moons are different, showing a mix of old, dark areas with many pits and lighter, younger areas. There is evidence of geological activity, past or present, on some of these moons. JUICE will examine how active the moons are now and consider how active they may have been in the past. Composition and development of the moons. JUICE wants to paint a detailed picture of how the mass of these moons is distributed internally, how their interior has developed over time, and whether they have experienced tectonics. The second mystery we're looking at is seen in the upper left. Why is Ganymede so unique? Ganymede, here in a nice image by NOAA, is the largest moon in the solar system. It is the main science objective of the JUICE mission. This is the moon the probe will orbit in the final part of the mission and the moon on which it will eventually crash. The focus will be on the magnetic field. ESA finds this moon especially interesting, in part because it's the only moon in our solar system that has an intrinsic magnetic field, and that within the larger magnetic field of Jupiter. These magnetic fields interact in a special way. Surface and ocean. Ganymede has a surface of different ages, from very old to fairly recent. This makes it interesting to compare this moon with the other 2 moons. With the radar on board, I'll tell you a little bit more about JUICE's instrument in the second part of my story. The probe will try to penetrate the thick ice crust to study its ocean. The atmosphere. JUICE will also study the water vapor and other substances in Ganymede's thin atmosphere to understand the processes in the Moon's environment. Furthermore, they will conduct studies of the ice moon's rotation, gravity, shape, and internal structure. The third mystery ESA wants to unravel you see in the middle. How has Jupiter's complex environment formed its moons, and vice versa? To answer this question, ESA focuses on the complicated interactions between the moons themselves and those with their parent planet. The interaction, which you see here in an animation, comes from an environment of intense magnetism and radiation. This environment creates plasmas and extremely fast-moving particles. This causes things like auroras on Jupiter and several moons, hotspots and belts of intense radiation. Parts of the plasma in this environment is hurled towards the moons Europa and Ganymede. A complex gravitational environment. This environment influences the orbits of all 4 Galilean moons. For example, there's a so-called 1 to 2 to 4 Laplace resonance. For every orbit Ganymede travels, Europa travels 2 and Io travels 4. JUICE will investigate not only how these interactions work, but also what the effects are on the habitability of the moons. The fourth mystery ESA wants to investigate is shown on the lower right. Could there be, or ever have been, life in the Jupiter system? ESA aims to answer this question by focusing on looking at the ice moons as possible habitats due to the presence of the conditions required for the emergence of life, such as hidden oceans, magnetism, heating by tides, which in turn are caused by the strong gravity of Jupiter, the composition of the moons, and possible atmospheres. The presence of elements important to life such as carbon, oxygen, nitrogen, magnesium, and iron will also be examined in great detail. By studying these topics, scientists hope to not only say something about these moons as possible habitats, they also hope to better predict habitability of similar planetary systems around other stars. The last mystery ESA wants to investigate with JUICE can be seen in the upper right. What is a typical gas giant planet like? How did it form and how does it work? ESA intends to answer this question by focusing on looking at the Jupiter system as not only an archetype for the gas giants of the solar system, but also for the many giant planets now known to orbit other stars than our Sun. One of JUICE's main goals is to understand how gas giant planets and their moons are formed. And ESA is also keen to understand how such planetary systems evolve. Answering these questions will not only provide insight into how such a planetary system and its components have formed and evolved over time. It also sheds light on how potentially habitable environments may form in Jupiter or Jupiter-like systems in the solar system and beyond. So now that we know what they hope to discover with the JUICE mission, we can answer the second question I asked at the beginning of my story. What instruments do they tend to use to make those discoveries? JUICE has to do its work in an extreme environment. This has had important implications for the probe's design. The main factors here are the great distance from the Sun. Sunlight is 25 times weaker than on Earth due to that distance. The solar panels therefore have a huge surface area of about 85 square meters to capture enough light. The large temperature differences JUICE has to deal with. It's plus 250 degrees Celsius at a Venus flyby and minus 230 degrees Celsius in the Jupiter environment. Multiple layers of insulation totaling 100 kilograms keep the probe's temperature stable. The probe has to operate in an environment with intense radiation. Special shields have been developed and installed to protect the electronic equipment. And the large distance from Earth averaging something around 700 million kilometers, not only affects the amount of light JUICE can capture, it also complicates communication with Earth. Therefore, there's a 2.5-meter antenna on it. And there's also a computer on board to solve problems independently. A signal simply takes too long, about 48 minutes on average, one way, to intervene in time if needed. For the research, there are 10 state-of-the-art instruments on board, divided into 3 groups. The first group is a group of remote sensing instruments, so instruments that can make remote measurements. They mainly map global and local processes, such as Jupiter's clouds, temperature, the icy surfaces of the moons, and the atmospheres of Jupiter and the ice moons. Among these instruments, you will find an optical camera. That's a camera that takes pictures in visible light, so the light that the human eye can see too. 2 spectrographs. Those are instruments to break up light into different colors and study the light in that way. And a special type of radio telescope. The second group is a group of geophysical instruments, which examine the surface and subsurface of the moons, look at the atmospheres of Jupiter and the moons in a different way, and measure gravitational fields. Among these instruments, you will find a laser altimeter, which measures altitude very precisely with laser beams, a specialized type of radar that can look below the surface, and a radio science experiment. The third group is a group of so-called in situ instruments, which can look in situ at the behavior of particles, the magnetic field, radiation and plasma environment of Jupiter and the ice moons. In addition, there's an experiment on board. Using several telescopes on Earth, they will try to accurately determine the position and speed of the probe with this instrument. Now, of course, JUICE was folded for launch so that the probe would fit into the nose cone of the Ariane 5 rocket. If all went according to plan, the probe would be unfolded in a period of 50 minutes to 17 days after launch. But this didn't quite work out right away. With the 16-meter-long RHIME instrument, that's the long antenna on top of JUICE in the video that I will play in a bit, things initially went wrong. RHIME was folded into 2 parts, each containing 4 segments. The second segment did not unfold properly, so part of the antenna remained stuck. Several solutions were tried, including heating and sort of shaking it loose. Finally, together with the manufacturer of the antenna, the solution was found and the antenna came loose. How JUICE completely unfolded can be seen in this somewhat accelerated video. And this is the RHIME instrument that was stuck for a while. In this configuration, JUICE is now on its way along the route Theo described earlier, on its way to undoubtedly great discoveries. Thank you very much for your attention.
Well, thank you very much, Sarah. Very interesting presentation. And the big question is, of course, will all the information that is thought about that JUICE will collect from the moons and from Jupiter, will that actually happen in 7 or 8 years from now?
Yeah, that's a very big question. Let's hope so.
Yeah. Let's look at the questions. There's a question from Peter van der Wijst, and he's asking, are you not concerned about contaminating Ganymede with Earth life on JUICE when it will crash?
Yeah, that's a very good question. And it's actually a question I heard when I went to the press conference before the launch. There's someone that asked exactly that question. And the answer was no. That's the short answer. And that's because the ice crust on Ganymede, is very thick. And so there's no life on the surface. So they do not expect to contaminate the moon in that way. So that's the answer ESA gave. Let's hope they're right. They probably are.
But do they have certain precautions that any sort of life on the juice will be removed, or that they have taken certain things? Although it has been in space, of course, so the chance that it stays live there is not that high. But
Yeah, but still, yeah, you have small, yeah, life that can remain on it, that is very resilient. Yeah, like all space probes, it was manufactured in a very clean environment, a clean
yeah,
room. But from what I know, it was not in a. You have these grades of clean rooms. Like if something goes to Mars and it will be driving around, then there's more cleanness in that room than the
yeah,
room Juice was built in. But they're not expecting any problems. So yeah.
yeah. Well, let's hope that it will not be contaminated. It will be a
Well,
shame, of
let's hope.
course. Yeah. And the second question is, you mentioned about Jupiter with all these magnetic fields.
Mhm.
Any idea how they have measured that these large magnetic fields are around Jupiter?
Yeah, so there is several ways that they already know that the magnetic fields are strong, and one of them is by through observations by other spacecraft that have been near Jupiter. So, for example, NASA's Juno mission, it's
Hmm.
still at Jupiter. Um, One of the goals of that mission was to map the magnetic field of Jupiter and the magnetosphere. So that's a big source of information. But also earlier missions like Galileo and even Voyager already saw evidence of that. You can also look at the way the moons around Jupiter behave. That also says something about the
Hmm.
magnetism of Jupiter itself. And things like, for example, auroras also indicate magnetism because auroras are like disturbances of the magnetosphere.
Okay, yeah. So there are certain measurements that have been taken place, and so that's why they know about these magnetic fields. Yeah.
Yeah, and they're gonna look at it even better still. So
Yeah. And then the last question, what do you think the chance is that there will be life underneath the ice in the water, and how will they measure that?
yeah, so ESA itself does not expect to find life, or at least that's not. They say it's not equipped to detect life.
Hmm.
It's designed to look if the circumstances are there for life. So yeah, like oceans, like biologically essential elements.
Hmm.
But it's not equipped to detect life itself. So ESA says, how big is the chance? Well, there's none, or sort of. There might be some ways, like flying through plumes of water vapor. That might be a way.
Hmm.
And so, yeah, in that way, what I think is, I guess, what ESA says. Who am I to, doubt that? And looking below the surface of the ice crust can be done in different ways. There's a magnetometer. So the combination of two aspects. One is that salty water, and that is, of course, if the oceans of
Hmm.
those moons are salty. That's something they want to look at. But if the water is salty, and Jupiter's changing magnetic field, those are responsible for the creation of weak magnetic fields around these icy moons, and those can be measured with the magnetometer. Let me
Hmm.
pronounce it correctly.
Yeah.
And another way is with I told you about the altimeter, laser altimeter, so a laser that measures the altitude with a laser beam.
Hmm.
And if there's an ocean below the ice crust, there will be quite significant changes in the height that the laser is measuring. That would be if there's not an ocean, there's tiny differences, and if there is an ocean, the differences will be very big. So that's also a way they can at least see that there is water there. Yeah.
Okay, well, who knows? There will be life, and I understand that in a few years they will also launch another rocket, and one of them will actually land on one of those moons.
On Europa, right? Yeah,
Yeah, and then they
that's pretty
will
exciting.
drill through the ice, but I don't know if that's already something for sure or if that is something that they are planning to do. And then
Yeah,
with
I
kind of
heard
a
about it
submarine,
mentioned too. Yeah.
with the submarine, they want to go through the water underneath the ice. That will be a very interesting one.
A yellow submarine?
The yellow submarine, yes. Okay, thanks very much, Sarah. And you're the host, so you will tell a little bit about the next internet
Yes, I
broadcast.
will. I will wrap our story up nicely. Yes.
Thank you.
Yeah. Yeah, so this was the second broadcast of this season, the season 23-24. And every season we provide a digital evening broadcast once every 2 months, usually in Dutch, and usually from the Leiden Observatory. Our next broadcast is in Dutch on Thursday, November 16th at 8:30 in the evening. This one will be about a very interesting subject, the dark universe, so dark matter and dark energy. If you want to know more about the upcoming and next broadcasts, check the calendar on our website or the one on the website of the Old Observatory. And you can find the addresses on the final slide. You can see it here already of this broadcast. And of course, you can follow us on Facebook. So thank you very much for your attention. I hope you learned something. Have a nice evening and see you next time.